The rapid advancements in 5G network technologies have transformed the operational paradigms of modern vehicular services and applications. Autonomous vehicles, in particular, represent intricate systems that integrate various technologies, including perception algorithms, path planning, control theory, and vehicle positioning. Trajectory prediction is a crucial research domain, playing a vital role in the decision-making processes of intelligent vehicles. Currently, trajectory prediction is primarily driven by neural network approaches, with recurrent neural networks, RNNs, being the most prominent. However, trajectory prediction faces significant challenges in real-world scenarios, particularly in traditional telematics environments. These challenges include the lack of complete trust in multiple parties, uncertainty in participant data quality, and extensive prediction delays. Federated learning, FL, presents a viable strategy for addressing these challenges while preserving data privacy in distributed settings. By leveraging the inherent features of blockchain technology, such as tamper resistance, anonymity, and traceability, Florida establishes a robust foundation for efficient and reliable data sharing among participants. This paper proposes a novel asynchronous federated learning data sharing method, utilizing an interpretable reputation quantization mechanism and graph neural network tools. The proposed method enables data providers to share data structures under differential privacy constraints, ensuring security while reducing redundant data. Deep reinforcement learning is implemented to categorize vehicles by reputation level, optimizing the aggregation efficiency of federated learning. Experimental results demonstrate that the proposed data sharing scheme reinforces the security of the trajectory prediction task while enhancing prediction accuracy. The method addresses the challenges in trajectory prediction by providing a robust foundation for efficient and reliable data sharing among participants, ensuring data integrity, maintaining anonymity, and providing traceability. The proposed method employs a graph neural network, GNN, to quantify the reputation of each data provider, allowing for the identification of high-quality data sources. The GNN is trained using a reinforcement learning algorithm, which optimizes the reputation quantization mechanism. The resulting reputation scores are used to weight the contributions of each data provider, ensuring that high-quality data sources have a greater impact on the federated learning process. The proposed method has been evaluated using a real-world dataset, demonstrating its effectiveness in enhancing the security and accuracy of trajectory prediction in autonomous driving applications. The results show that the proposed method outperforms traditional federated learning approaches, achieving higher prediction accuracy and improved security. In conclusion, the proposed asynchronous federated learning data sharing method offers a promising solution for enhancing the security and accuracy of trajectory prediction in autonomous driving applications. By leveraging an interpretable reputation quantization mechanism and graph neural network tools, it addresses the challenges of multi-party mistrust, data quality uncertainty, and prediction delays, ultimately paving the way for more efficient and reliable data sharing among participants. The conventional approach to handling delays in heterogeneous vehicle data relies on federated learning-enabled blockchain technology, which has several limitations. To address these, a novel trajectory prediction approach, RAFLTP, based on graph neural networks, is introduced. This approach incorporates an asynchronous Florida strategy based on reputation evaluation to quantify vehicle reputation through interactions between vehicles. The RAFLTP framework includes a reputation reward mechanism that replaces the traditional loss function with reputation values computed from vehicle trajectory data, driving the method components to cooperate in promoting federated learning to train more instructive global models. A reputation-driven asynchronous Florida scheme adapted to dynamic and heterogeneous vehicle networks is also proposed, complemented by a reputation-enhanced proximal policy optimization (PPO) algorithm that groups vehicle trajectory models based on reputation values to reduce the Florida cost. Differential privacy techniques are employed to enhance the privacy and security of shared trajectory graph models and vehicle reputation values while preserving the graph structure and interactions among vehicles. The proposed approach is evaluated through extensive experiments on two large-scale vehicle trajectory datasets, NGSIM and ApolloScape, with different real-world scenarios, demonstrating its effectiveness in ensuring data security, enhancing trajectory prediction accuracy, and adapting well to various traffic scenarios. The paper addresses the inefficiency and poor security of current trajectory prediction methods in vehicle-to-vehicle and vehicle-to-infrastructure communication. It proposes a new asynchronous federated learning (FL) model for trajectory prediction, which addresses the problems of inefficient training and privacy leakage in existing methods. The proposed data sharing architecture comprises a permissioned blockchain module and an Florida module. The permissioned blockchain handles retrieval and data sharing transactions without recording raw data. The Florida module utilizes a graph-based approach for model training and data sharing, involving vehicle authentication, data sharing requests, and the collection of weighted graph models perturbed with differential privacy noise. The paper also introduces a reputation-based hybrid blockchain for data sharing, where vehicles compute reputation values based on the original data to assess the quality of their trajectory data. These values are recorded as shared transactions and in the local models of other participating vehicles within each vehicle's local directed acyclic graph, DAG. The proximal policy optimization (PPO) algorithm is used to group vehicles based on the reputation evaluation mechanism, prioritizing high-quality vehicle clusters in deep aggregation. The supernodes collaborate to train the global model through asynchronous Florida and broadcast the results to all committee nodes, which are charged with driving the consensus process for the permissioned blockchain. The vehicles optimize their local models by integrating the global model, thereby achieving increased accuracy in predicting trajectories. A novel methodology for enhancing vehicle trajectory prediction in autonomous driving systems is presented, integrating reinforcement learning, federated learning, and differential privacy to improve prediction accuracy while safeguarding data privacy. The approach utilizes undirected graphs to represent interactions between objects, where each node denotes a vehicle trajectory and edges signify spatial interactions. A graph convolution network (GCN) processes this data, capturing both spatial and temporal features. A twolayer gated recurrent unit (GRU) network serves as both the encoder and decoder for the trajectory prediction model, enabling the effective modeling of sequential data. To facilitate secure data sharing among distributed multi-users, the authors propose a blockchain-based mechanism for storing and verifying data profiles, ensuring that raw data remains on local vehicles and preventing privacy leakage. Furthermore, a differential privacy-enhanced data sharing method is introduced, leveraging graph neural networks for quality verification. This approach improves computational and storage efficiency while preserving structural and contextual information. The proposed methodology has the potential to significantly enhance prediction accuracy and data privacy in autonomous vehicle systems. The integration of reinforcement learning, federated learning, and differential privacy enables the development of a secure and efficient vehicle trajectory prediction model. This approach can be applied to various autonomous driving scenarios, improving the overall safety and reliability of autonomous vehicle systems. The use of graph neural networks and blockchain technology ensures the secure and efficient sharing of data, while maintaining the privacy of individual vehicles. A novel reputation-aware data sharing mechanism for vehicle-to-vehicle communication in IoT networks is proposed to enhance data sharing efficiency and privacy. Leveraging blockchain technology for secure data exchange. This mechanism utilizes a novel evaluation metric based on trajectory similarity among vehicles. This metric considers velocity, position, and orientation differences to determine the relevance of shared data, thereby improving its quality, accuracy, and reliability. When a user requests data from a nearby node, all nodes within the same community broadcast this request to other vehicles observing the target during that timestamp. This process recursively collects vehicles with structural stability, minimal redundancy, and no anomalous data. To protect privacy, differential privacy is applied to each local model using the Laplace mechanism. Participants transmit their models as blockchain transactions to other participants for federated learning. Upon receiving a model, a participant trains a new local data model based on the received model and their local data, and broadcasts this new model to other participants. This iterative process continues among participants, ultimately generating a global model. The reputation value derived from trajectory similarity among vehicles serves as an evaluation metric in this system. Calculated using the normalized dissimilarity between two trajectory segments, this metric considers differences in velocity, position, and orientation. By incorporating trajectory similarity into reputation calculations, the system promotes location awareness and enhances data relevance, thereby improving the overall efficiency and effectiveness of data sharing in vehicle-to-vehicle communication networks. This approach ensures secure, private, and efficient data sharing, enabling reliable decision-making in IoT networks. In a subjective logic framework, local opinion vectors omega I right pointing arrow j are introduced to describe the reputation between two vehicles, v and vj. These vectors comprise trust re right pointing arrow j, distrust d right pointing arrow j, and uncertainty ui right pointing arrow j, calculated from positive and negative events, beta and alpha, respectively. The uncertainty ui right pointing arrow j depends on the communication quality c right pointing arrow j between vehicles. To form a common opinion omega rec x right pointing arrow j, local opinions are combined with suggested opinions from neighboring vehicles, weighted by their recommender vehicles. The final opinion omega final x right pointing arrow j is then formed by combining the local opinion with the common opinion, considering uncertainty and trust values. Reputation value re right pointing arrow j is calculated as the expected belief of v in providing true relevant data to vj, expressed as re right pointing arrow j equals re right pointing arrow j plus gamma ui right pointing arrow j, where gamma is a constant measuring uncertainty's impact on reputation, initially set to 0.5. Reputation values are incorporated into a directed acyclic graph, DAG, as training model parameters, enabling node connections and the propagation of updated DAGs among vehicles. This scheme achieves loose consistency among vehicles with lower computational intensity and increased global robustness. To address the high computational and communication costs of prevailing consensus mechanisms like proof of work, POW, the authors propose a consensus mechanism called proof of reputation, POR. POR combines vehicle reputation values with the consensus process, enhancing node computational resources. Committee members are chosen based on their reputation scores, and the consensus process involves verifying and measuring the quality of local data models during trajectory prediction training. The total loss of the trained local models is calculated as loss equals 1, TTXT equals 1, YT pred YTGT, where T is the future time step, and YT pred and YTGT are the predicted position and ground truth at time step T, respectively. During the consensus process, committee nodes exchange trained models and corresponding losses, recording the transmission as a model transaction along with its corresponding loss. In the Internet of Vehicles (IOV) context, this research proposes a novel approach to enhance asynchronous federated learning for trajectory prediction tasks. A reputation-driven proximal policy optimization (PPO) vehicle clustering algorithm is introduced to optimize global model aggregation and improve local models. The approach begins with a reputation evaluation mechanism that utilizes differential privacy to validate model updates received from participating vehicles. This mechanism eliminates data redundancy and ensures the privacy of vehicle trajectory data. Reputation values calculated from private track data are used to group vehicles based on their performance and reliability. An enhanced asynchronous federated learning mechanism integrates the proposed reputation evaluation mechanism with the PPO algorithm. This approach addresses challenges of insufficient heterogeneous model aggregation and significant global model update delays in traditional federated learning. By grouping vehicles into clusters based on reputation scores, the asynchronous learning process is optimized, leading to improved learning performance and reduced communication costs. A graph distribution feature represents the vehicle's local model and database, updated based on the explanatory reputation score, reflecting the vehicle's reliability and performance in the federated learning system. Deep reinforcement learning (DRL) agents learn optimal reputation thresholds for vehicle grouping, improving the overall efficiency of the federated learning process. The proposed approach contributes to the development of more efficient and secure federated learning mechanisms for trajectory prediction tasks in the IOV. This research has the potential to enhance the accuracy and reliability of vehicle trajectory predictions while protecting private data and improving system efficiency. The method's novelty lies in its ability to balance model performance and data privacy, addressing a critical challenge in IOV applications. Key benefits of the proposed approach include improved learning performance, reduced communication costs, and enhanced data privacy. The integration of reputation evaluation in PPO algorithms enables efficient and secure federated learning, making it suitable for large-scale IOV applications. In vehicular networks, traditional asynchronous federated learning (FL) approaches struggle to adapt to dynamic traffic conditions and optimize local prediction models. To overcome this limitation, the authors propose a novel approach that employs the proximal policy optimization (PPO) algorithm with a reputation-driven reward feedback mechanism. This mechanism prioritizes the deep aggregation of high-reputation vehicles, leading to a superior global aggregation model. The reputation of learning (ROL) is introduced to quantify a vehicle's reputation value in the aggregation process, calculated as the sum of the product of the completed combined model in a slot, the training data of a vehicle, and the local learning time cost of the vehicle. The total cost of FL in a time slot is given by the sum of the ROL and the total time consumption, including the local learning time cost and communication cost of each vehicle. To minimize execution time and enhance model accuracy, the authors propose a PPO-based node clustering algorithm that categorizes vehicle nodes according to their reputation values. Within a specific timestamp, the algorithm selects participating vehicles based on reputation values until each grouping contains no more than n vehicles. This approach prioritizes the aggregation of trajectory graphs with high reputation, representing high data quality, and improves the global aggregation model. The node selection task is formulated as a Markov decision process, where the system state is represented by the wireless data rate between vehicles, available computing resources, reputation of vehicles, and selection state of vehicles. The action taken at each time slot corresponds to a vehicle selection decision, which can be framed as a O1 problem. The customized reward function adds 1 to the reward value for choosing vehicles with high reputation values, ensuring the aggregation of high reputation vehicles and improved model accuracy. Accurate prediction of vehicle trajectories is crucial for the safety and efficiency of autonomous driving systems, particularly in complex and dynamic traffic environments. Existing approaches to trajectory prediction, however, are often limited by their inability to handle diverse traffic conditions and uncertain environments. To address these challenges, researchers have developed a novel deep learning model, RAFLTP, which leverages a reputation-based fusion strategy to integrate vehicle features from various sources and prioritize high reputation data for enhanced accuracy. The RAFLTP model consists of 2 main components, a reputation-based fusion module and a deep learning predictor. The fusion module aggregates vehicle features from different sources, assigns reputation scores based on their reliability, and prioritizes high reputation data for the prediction task. The deep learning predictor utilizes a neural network architecture to forecast future trajectories based on the fused features. A reinforcement learning framework is used to optimize the RAFLTP model, involving a reward function that assesses the model's performance and adjusts parameters to maximize cumulative rewards over time. The reward function is defined as a weighted sum of the model's accuracy and efficiency, with the weights adjusted to prioritize accuracy in complex scenarios. The optimization process involves updating the model's parameters using a policy gradient method, with the goal of maximizing the cumulative reward over time. The RAFLTP model is evaluated on 2 well-known datasets, NGSIM and Apollo-Scape trajectory, and compared to a baseline method, social GAN, using metrics such as root mean square error, RMSE, average displacement error, AID, and final displacement error, FDE. The results show that RAFLTP outperforms the baseline in all 3 metrics, demonstrating its effectiveness in predicting vehicle trajectories. Ablation studies reveal that the reputation-based fusion strategy and the reinforcement learning optimization are crucial for achieving high accuracy in trajectory prediction. The authors note that the RAFLTP model has limitations, including the need for more diverse and extensive datasets to further improve its robustness and generalizability. Future work will focus on addressing these limitations and exploring the application of RAFLTP in real-world autonomous driving systems. The proposed methodology, which integrates a GRUBASED network with reinforcement learning and differential privacy, is evaluated through several experiments. Results presented in Fig. 6 show that the basic encoder-decoder network has the highest error due to its limited consideration of vehicle interactions. However, incorporating GRIB-based model enhancements under the proposed method significantly reduces the error. The reputation-based PPO module is crucial, as its absence results in a substantial increase in error. Differential privacy also plays a key role, filtering out abnormal and redundant data, leading to more robust and secure model aggregation. The absence of federated learning, FL, leads to lower prediction accuracy, emphasizing the effectiveness of reputation-based grouping aggregation in alleviating the challenges associated with heterogeneous data fusion and enhancing trajectory prediction accuracy. Prioritizing the aggregation of vehicles with low reputation values, however, reduces the trajectory prediction accuracy. The influence of deep reinforcement learning, DRL, methods is investigated by comparing the learning results of the PPO algorithm and the DQN algorithm in the NGSIM and ApolloScape datasets. Figs. 7 and 8 demonstrate that the PPO algorithm is more stable and adaptable to changes in both datasets, converging quickly after positive feedback. The training time of the PPO algorithm is 34.5% faster than that of the DQN algorithm. The impact of bad nodes on different modules within the overall framework is analyzed by introducing anomalies in the data providers. Figs. 9 and 10 show that an increase in the number of bad nodes significantly degrades performance. The proposed methodology, which incorporates a reputation-based PPO module and differential privacy, is more robust to bad nodes compared to the baseline methods. The results demonstrate that the proposed method can effectively handle heterogeneous data fusion and alleviate the challenges associated with bad nodes. This section of the research paper delves into the proposed federated learning framework for trajectory prediction in vehicular networks. The authors investigate the impact of various parameters on the model's accuracy and efficiency. They first examine the effect of differential privacy module invocation frequency on the average distance error, AID, of trajectory prediction. Higher invocation frequencies lead to improved prediction accuracy, as shown in Figure 11. The results in Figure 12 demonstrate that increasing the global aggregation frequency also enhances prediction accuracy. The paper also explores the impact of the private budget, denoted by E, on the AID of trajectory prediction. The authors investigate the effect of varying E from 0.1 to 1.0 across different datasets. As depicted in Figure 13, the results indicate that E equals 0.3 strikes a balance between data privacy and utility in the ApolloScape dataset, while E equals 0.4 is required in the NGSIM dataset to maintain this balance. In addition, the authors investigate the superiority of their proposed interpretable reputation reward mechanism as a quantitative metric for optimizing federated learning. The results in Figure 14 demonstrate that the traditional synchronous federated learning scheme yields inferior prediction results compared to the authors' proposed asynchronous federated learning, AFL, scheme. The authors also show that substituting RMSE for reputation values in reinforcement learning-based vehicle grouping results in a reduction in trajectory prediction accuracy. The authors attribute the improvement in prediction accuracy to the reinforcement learning-based grouping of vehicles according to their reputation scores, which directs low-quality data providers to a shallow aggregation group and subsequently improves prediction accuracy. The differential privacy module is also shown to be effective in constraining the data structures shared by data providers, limiting the impact of anomalous data nodes and redundant nodes on prediction accuracy. Overall, this section of the paper provides a comprehensive analysis of the proposed federated learning framework, highlighting the importance of differential privacy, aggregation frequency, and reputation quantization mechanism in achieving accurate and efficient trajectory prediction in vehicular networks. The proposed trajectory prediction model, GRIP++, is evaluated through a series of experiments and comparisons with state-of-the-art methods. Figure 15 visualizes predicted trajectories under various traffic scenarios, showcasing GRIP++'s effectiveness in predicting vehicle trajectories. The blue dashed line represents the prediction result of GRIP++, while the green dashed line represents the prediction result of GRIP. The observed history and future ground truth are depicted by the purple solid line and red solid line, respectively. The vehicle reputation quantification mechanism in GRIP++ addresses potential biases in trajectory prediction by focusing on the quality of vehicle data and the similarity of local trajectories. This enables the aggregation of clusters of vehicles with high-quality data and similar trajectory model structure. A comparison analysis with 7 baseline methods, including encoder-decoder, CSLSTM, TRA-P-HIC, social GAN, GRIP, spectral, and DGI-NET, demonstrates GRIP++'s competitive performance. As shown in Table 2, GRIP++ outperforms GRIP by reducing the average displacement error, AID, by 11.2% and the final displacement error, FDE, by 10.2% on the ApolloScape dataset, surpassing the spectral result. Notably, GRIP++ predicts trajectories for all vehicles in a traffic scenario, unlike spectral, which predicts only a single vehicle's trajectory. This highlights GRIP++'s advantage in handling complex traffic scenarios. The approach's limitations are acknowledged, including the potential for biases in trajectory prediction. However, the importance of considering the quality of vehicle data and the similarity of local trajectories in aggregating clusters of vehicles is emphasized. The paper introduces a groundbreaking framework for distributed trajectory prediction in autonomous vehicles, leveraging graph neural networks and asynchronous federated learning. This novel approach, RAFLTP, utilizes a reputation quantization mechanism to ensure data security and efficiency. Experimental results demonstrate that RAFLTP outperforms existing methods, including GRIP and GRIP++, in terms of prediction accuracy and tolerance to bad nodes. A comparative analysis of the average performance of various methods on the ApolloScape and NGSIM datasets is presented in Table 2. RAFLTP achieves the lowest average displacement error, AID, and final displacement error, FDE, on both datasets, indicating its superior predictive performance. Figure 15 visualizes the prediction results under various scenarios, showing RAFLTP's robustness to different traffic conditions. The computational efficiency of RAFLTP is evaluated in Table 3, reporting the prediction time for 1,000 vehicles with batch sizes of 128 and 1. Although RAFLTP incurs a delay compared to GRIP++, its computational time remains acceptable compared to other methods. The proposed approach provides data privacy protection and higher prediction accuracy, making it a suitable solution for autonomous vehicles. The paper concludes by highlighting the significance of the proposed framework and its potential for future research. The authors plan to focus on integrating RAFLTP with 6G networks and further enhancing its efficiency. The authors present a comprehensive review of the literature on federated learning, reinforcement learning, and trajectory prediction in intelligent transportation systems. They discuss various approaches to federated learning, including those proposed by 13, 14, and 15, which focus on deep reinforcement learning and task scheduling in heterogeneous autonomous robotic systems. Additionally, they highlight the concept of blockchain-based decentralized trust management in vehicular networks, as proposed by 26 and 27. The authors also review the literature on trajectory prediction, including works by 19, 20, 21, 22, and 23, which utilize convolutional social pooling, social STGCNN, and DAGNet. Furthermore, they mention the work of 24 on predicting motion of vulnerable road users using high-definition maps and efficient ConvNets. In the context of federated learning, the authors discuss approaches proposed by 36, 37, and 38, which focus on ultra-reliable low-latency V2V communications. They also mention the work of 39 on asynchronous minibatch algorithms for regularized stochastic optimization and the privacy-preserving deep learning approach proposed by 40. The authors examine various privacy-preserving techniques, including differential privacy, L-diversity, and additively homomorphic encryption, as proposed by 41, 42, and 43. They also mention the work of 44 on differentially private data publishing and analysis and the graph-based interaction-aware trajectory prediction approach proposed by 45. The review also covers blockchain-based systems, including peer-to-peer information systems, cryptography, and smart contracts, as proposed by 46, 47, and 48. The authors mention the work of 49 on asynchronous federated learning with directed acyclic graph-based blockchain in edge computing and the U.S. Highway 101 dataset proposed by 50. The authors highlight the key contributions and limitations of each approach, providing a comprehensive overview of the literature on federated learning, reinforcement learning, trajectory prediction, and blockchain-based systems. The authors expand on previous research in trajectory prediction, referencing notable studies such as DGI-NET and Traffic, which utilize dynamic graph and interaction-aware convolutional networks, and weighted interactions for trajectory prediction in dense and heterogeneous traffic, respectively. They also acknowledge the significance of prioritized trajectory replay in proximal policy optimization, as demonstrated in PTR-PPO. Their proposed methodology is grounded in graph-based trajectory prediction, where the graph structure captures complex interactions between agents. This approach is motivated by the understanding that real-world traffic scenarios often involve intricate relationships between vehicles, pedestrians, and other agents. The graph-based formulation enables the modeling of these interactions and their impact on trajectory prediction. The authors introduce a novel graph attention mechanism, integrated into a graph convolutional network, GCN, architecture. This mechanism allows for adaptive weighting of the importance of neighboring agents, enhancing the model's ability to capture nuanced interactions. The GCN architecture processes graph-structured data, effectively aggregating information from neighboring agents. They also propose a novel loss function, jointly optimizing trajectory prediction and interaction modeling. This loss function consists of two components: a trajectory prediction loss, measuring the difference between predicted and ground truth trajectories, and an interaction modeling loss, encouraging the model to learn meaningful interactions between agents. Experimental results demonstrate the efficacy of the proposed methodology, with the author's model outperforming baseline approaches in terms of trajectory prediction accuracy. The results highlight the importance of the graph attention mechanism and the novel loss function in capturing complex interactions and improving prediction performance. The authors acknowledge certain limitations of their approach, including the assumption of a fixed graph structure and the potential for oversmoothing in the GCN architecture. Future work involves addressing these limitations and exploring the application of the proposed methodology to more diverse and complex traffic scenarios.